Okay, for this one, now let's go ahead and actually run the chi-squared goodness of fit test. Now that we've showed how to do it by hand, we haven't checked to see um, what this value means, 4.77. So we're going to run a goodness of fit test. And here are the steps to run a goodness of fit test. Step 1, of course, null and alternative hypothesis, H1, 0, H1. That it follows a certain distribution as described, and it does not follow. Pick a level of significance. That's always what we got. Step 3 is a little bit longer for doing it by hand. You have to calculate the expected values the way I did. Do this table of values, and you end up with a test statistic if you do it by hand, which we did. After you have the test statistic, what you do is then you would take this test statistic and then determine, step 4, where is that? From the test statistic, you determine the p-value, and then you go ahead and make a decision. And so you would follow that same format that we've done on other ones. In this case, your degrees of freedom are k minus 1, or k is the number of categories we have, right? And so this is 1, 2, 3, that's 6. So the degrees of freedom would be 5. So now that we have this actual chi-squared, what you would do, there's one way here, is you would do calculator chi-squared. Degrees of freedom is, there were 6 colors, minus 1 is 5, and you want the probability that it's greater than 4.77. I think that's what we got. And so, yeah, 4.77. And so your p-value is 0.444. So it's not greater than 1. So we failed to reject the distribution there. Failed to reject the null hypothesis. Another way to do it would be to enter these values in here, the observed and expected, using StatCruncher. Here's your observed values. Here's your expected. You put them in, and you run a goodness of fit test, chi-square. And in there, what you're doing is the observed. It's that simple. And then you go ahead and then compute. And then what you get here is, there's your chi-square value and your p-value like I had just done. And so with that p-value 0.445, what does that mean? Since the value is greater than some significance value of 0.05, 0.01, you do not reject the null hypothesis. So we're saying that it's very possible that what we observed is what we expect. Even though the numbers aren't identical, it's close enough to say that we don't have enough evidence to reject, so we do not reject. So that's how you would do it, and that's a goodness of fit test. And now here's some notes here about these, what's called this chi-square distribution. It's like the normal curve and the z-values, but again, because we're doing a different calculation, we don't need to fully understand like the graphs. This is like we do with normal, but again, just be aware of that these numbers don't just come out of, it's not magic. They come from the distribution of these of the chi-squared value depending upon how many categories. And so you have these characteristics you can get down from your notes, or you get down from the PowerPoint, or from here. But again, you can see the chi-square difference is not necessarily symmetric until we have large sample sizes, or the number of categories or degrees of freedoms increase. But you can see kind of how the distribution changes based on number of degrees of freedom. Let's do one more example here, or I actually have one more example here, looking at here's the situation from the notes. What's the expected values? Well, there's 1,500 sample size, so you're just taking the 7%, 8.6%. Take the percent of 1,500, and that's your expected, what you would expect out of 1,500 based off of these percents. And then now, if we want to know, an economist wants to know if the income distribution is still changing, or is it changing. So he redoes a survey of another 1,500 people and then gets this here. And so this would be what we call the observed right here, right? This is the observed, and then we're comparing that to the expected. And so the null hypothesis is that the observed data follows the 2000 distribution, and the null hypothesis is that it doesn't. And so we would run that hypothesis test again, or this goodness of fit hypothesis test. We need the chi-square. See, we don't want to do all that hand calculations. That's why StatCrunch is, I think, better in this case. And so I have the values in already here. In this was for the expected income, and then this was the observed income, and we're comparing those two. And so when you go stat goodness of fit chi-squared again, the observed is in observed income, and then the expected is in the expected income. I have them backwards. Just make sure you know which one's observed and which one's expected. The expected was this one here. Do I have that right? Let's double check. The expected, oh, I do have it wrong here. So this was the, let's do this again, the observed income, and this was the expected income. So don't make those mistakes. Expected income, stat goodness of fit test chi-squared, observed income, expected income, and then compute, and then you get a chi-squared of 10.1 and 0.12. 10.1 and 0.12. And again, so we go through that process here because the p-value, that's a p-value, because the p-value is greater than alpha, which is, do we have a significance test here somewhere? Oh, at the 0.05 level. Because of that, here, this is the p-value. Right here, the p-value is this here. Do not reject H0 since 0.1203 is greater than 0.05, right? So we don't have significant evidence to say that this has changed, right? It does not follow. We would say it kind of matches up. There's enough evidence to say that what we observe matches up to what would we expect to observe. And then if you want to do this last one on your own, but just make sure this is a little bit hard. I'm not going to run the test, but here's your observed, and the expected is 71.42 on this one. You would enter in observed and expected, again, because we would expect an equal distribution of births across the days, right? No one chooses the day to be born on. So if it's totally random, we would expect 71.42 births per day. And so you can see if this distribution follows what we would expect.